We all know that the world is not perfect. So why in the world would we expect for our conics to be perfect? What we're looking at now is we've already looked at our 3 different types of conics. What happens when they don't end up perfectly horizontal or vertical? Well, we have to look at a rotation of axes. So, the first thing we're going to do before we look at rotating our axes is how can we identify conic sections without completing the square? So, how can we identify a conic section without putting it in standard form, in other words? Because we don't always need to go through all that, at least not with rotating axes. So if you've got a conic section in this form, where you've got ax squared plus cy squared. Wait a minute, where's b? Oh, well, I don't guess we need it. It would be bxy plus cy squared plus dx plus ey plus f equals 0, in which a and c are not both 0, so one could be but not the other, then we can identify a conic section. If it ends up that a is equal to c, then we have a circle. If we multiply a times c and get 0, then we have a parabola. Basically, if a or c are 0, then it's a parabola. If a is not equal to c, but a times c is greater than 0, then we have an ellipse. And if a times c is less than 0, then the conic section is a hyperbola. So let's look at a few examples of this. In this case, a is 3 and c is 2. So a is not equal to c, so we don't have a circle. So we're going to multiply. A times c will be 3 times 2, or 6. Since 6 is greater than 0, then that means that we have an ellipse. Next, in this case, a is 1 and c is 1. So since a equals c, then we must have a circle. Here, a is, well, there's not 1, 0. And c is 1. So AC would be 0. Which means our conic section will be a parabola. And one more example here. A is 9 and C is negative 16. So if we multiply, we get a negative number. Since it's negative, then that means that our conic section is a hyperbola. And that's going to help us as we move forward through these rotation of axes. When you rotate axes, then you're taking the X and Y axes and you are, well, rotating them by some degree. In order to do that, then you've got to have X prime, Y prime. That's what these little apostrophes are called. So let's talk about this. Suppose an XY coordinate system and X prime, Y prime coordinate system have the same origin And theta is the angle from the positive x-axis to the positive x prime axis. Is there a picture of this? No. Let's draw a picture. So here's the x-axis and the y-axis. What's happening here is the x-axis is being rotated by some degree theta. And so is the y-axis, because they're both they're perpendicular still. So we're rotating the x and y axes to get a new coordinate system in order for our conics to not be along just the x and y axis. So if the coordinates of point P are x, y in the xy system and x prime, y prime in the rotated x prime, y prime system, then x is equal to x prime cosine theta minus y prime sine theta, and y is equal to x prime sine theta plus y prime cosine theta. So those are formulas that we're going to use in a second to help us out. So example 5 says, write the equation xy equals 2 in terms of a rotated system if the angle of rotation is 45 degrees. Okay, so if the angle of rotation is 45 degrees, then we can find x and y. X is x prime cosine of theta minus y prime sine of theta. So that would be x prime cosine of 45 degrees minus y prime sine of 45 degrees. What is cosine of 45 degrees? It's root 2 over 2. And sine of 45 degrees is also root 2 over 2. So x simplified would be root 2 over 2 times x prime, it was supposed to be a prime there, not a squared, minus y prime. Y is, let's do this in a different color. X prime sine theta plus y prime cosine theta. So we plug in our 45 degrees. And plug in for sine of 45 and cosine of 45. So simplified, that would be square root of 2 over 2 times x prime plus y prime. So what did we just find? Well, we found x and y in terms of x prime and y prime so that we can rotate our axes. What is the next step? We were told that the equation of this thing, we don't know what it is, maybe we should find that out, is xy equals 2. So we'll find out what this looks like in a bit. But what we do is we plug in what we just found for x and y. We found x to be square root of 2 over 2 times x prime minus y prime. And y to be square root of 2 over 2 times x prime plus y prime. What do we do with this? We simplify. So starting out, probably the best thing to do here would, let's take our root 2 over 2 and our root 2 over 2. Those are being multiplied, so let's go ahead and multiply them. That would give us 2/4. So we have 2/4 times x prime minus y prime times x prime plus y prime equals 2. Okay. 2/4 is 1/2. Then we FOIL. X prime minus y prime times x prime plus y prime would be x prime squared minus y prime squared. I know that's getting a little complicated in there. Equals 2. Keep simplifying by multiplying by 2. Well, let's see. We need to get, so multiply everything by 2. We've got x prime squared minus y prime squared equals 4. And in order to make this a conic in standard form, then we need to get this 4 to be a 1. So divide everything by 4. If we do that, then we've got x prime squared over 4 minus y prime squared over 4 equals 1. Now we can tell what this thing is. Since there's a minus in the middle, then this must be a hyperbola. It is a hyperbola where the transverse axis is, because x squared comes first, it is horizontal. Since there's no h and k, then we know that its center is at 0, 0. And we know that a squared is 4. So a must be 2. That puts our vertices 2 to the left and 2 to the right. So -2, 0, and 2, 0. Now, these are if our axis were not rotated, but it is. So looking at our picture here, our axis has been rotated 45 degrees. That means our x-axis now looks like this. And our y-axis now looks like this. So when we plot this, of course, 0, 0 is the same. So if our vertices are at -2 and 2, it was there and there. So now it's rotated down here and rotated up here. So something like that. It's really hard to tell exactly. And you're not going to have to graph these by hand. A long time ago, I used to do a lab with rotation of axes, and I just decided that was too much. You're welcome. So your hyperbola will look something like this. Again, you're not going to have to do these by hand. You'll have to do them in the with your graphing software online, but that'll be easier. So anyway, that's what it looks like, and there was our equation once it's changed. So as you can see, these are a little bit complicated and require quite a bit. You're going to see more algebra than just this to work them out. Now, in that first example, we were given our rotation. We were given the rotation to be 45. What do we do if we don't have the rotation? We find it using cotangent of 2 theta equals A minus C over B. There's our B. So now our equation is ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. So once we find our theta using cotangent of 2 theta equals a minus c over b, we can go back to finding x prime, y prime with the formulas we used in the last example. And this is just directions on what to do. So you can read through that and use it as you're working your problems. But where I'm just going to go forward and work an example here. It says, rewrite the equation 2x squared plus square root of 3xy plus y squared minus 2 equals 0 in a rotated system express the equation in the standard form of a conic section, and then graph it. So the first thing what we have to do is to find theta. Cotangent of 2 theta is equal to A minus C over B. So up here is what is A, B, and C. A is 2, C is 1, and B is the square root of 3. So we have cotangent of 2 theta is equal to 1 over the square root of 3. Now, how do we find theta from that? What we need to do is to put this cotangent in some terms that we can use. We know that cotangent is x over y. My pen's not working. There we go. Okay. So if we draw a picture of this where our angle is 2 theta, cotangent is x over y there. So start by finding c. So c squared will be 1 squared plus the square root of 3 squared. So c is the square root of 4 or 2. How is this helping us? Well, now we can put it into something where we can use our calculator to find the inverse sine or inverse cosine, because we can't find the inverse cotangent very easily. So cosine of 2 theta would be adjacent over hypotenuse. And the inverse cosine of 1/2 is 60 degrees. So that means theta is 30 degrees. So there, we've just been through all that, and we have found our angle of rotation, 30 degrees. The next step is to find x and y. So, x is, if you'll remember, x prime cosine theta minus y prime sine theta. And y is x prime sine theta plus y prime cosine theta. So plug in our 30 degrees. Cosine of 30 degrees is root 3 over 2. Sine of 30 degrees is 1/2. If we simplify that, simplifying it gets us pretty much square root of 3 times x prime minus y prime all over 2. And then for y, we've got x prime sine of 30 degrees plus y prime cosine of 30 degrees. I keep making that first one x squared. So sine of 30 is 1/2. Cosine 30 is root 3 over 2. So simplifying this one, there I did it again, would be x prime plus root 3 times y prime over 2. Next step is to plug in. So we're plugging in x and y into our original equation, which was 2x squared plus the square root of 3xy plus y squared minus 2 equals 0. So we've got 2 times x, which was squared, plus the square root of 3 times x times y. Plus y squared minus 2 equals 0. And yes, we have to simplify this thing in order to get it into standard form of a conic. So as you can see, we've got quite a mess to simplify. One of the hardest things about these problems is getting through all the simplification and not making a mistake that messes up the whole problem. So here we go. I'll have to write small here. So for this first one, we've got, on the bottom, we've got 2 squared, which is 4. On the top, we've got root 3 x prime minus y prime times root 3 x prime minus y prime. So we're foiling. If you need to go to the side and actually foil this on a scrap sheet of paper, please do that. So, because like I said, you do not want to make a mistake. But I'm not going to do that. I'm going to go ahead and tell you what it is here. But in the future, you're going to want to go to the side and make sure that you foil these absolutely correctly. So there's that. Then we've got square root of 3. And then 2 times 2 on the bottom is 4. And then we're foiling root 3 x prime minus y prime times x prime plus root 3 y prime. And we get this, root 3 x prime squared plus 3 x prime y prime. Let's make this bigger. Minus x prime y prime, which you could have went ahead and changed that to 2x prime y prime, but I didn't. Minus root 3 y prime squared. And then same thing over here. We need to square our x prime plus root 3 y prime. And on the bottom we'd have 4. So that gives us x prime squared plus 2 root 3 x prime y prime plus 3 y prime squared. Okay, next step is to get rid of the fraction. So, in order to do that, let's multiply everything by 4. And when we do that, it just gets rid of what's on the bottom. So we'll end up with 2 times what's on the top. It's times like these that I'm very thankful that I finally went out and bought one of the new iPads with the pencil, so I could write nice and small, nice and easily, because styluses were really getting on my nerves. Minus 8, because we multiplied by 4. There. And then distribute. So first we distribute the 2. So we've got 6 x prime squared minus 4 root 3 x prime y prime plus 2 y prime squared. Then distribute the root 3. So we get 3 x prime squared plus 3 root 3 x prime y prime minus root 3 x prime y prime minus 3 y prime squared. And then we've just got all this again because we didn't have to distribute through anything. Okay, next step is to get rid of some stuff, which is nice. We can cancel some things out. So I'm going to look at my x squareds first because we're combining like terms. So there's our x squareds. We've got 6, 3, and 1. So 6 plus 3 plus 1 is 10 x prime squared. Then let's look at the x prime y primes. Okay. So we've got, all these are root 3, so I'm not going to worry about the 3. So negative 4 plus 3, that's negative 1, minus 1, so that gives us negative 2, plus 2. Oh, yay, 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 yay. Our x prime y primes just went away. That's lovely. We like that. Okay, now let's look at the y squareds. So we've got 2 minus 3 plus 3. So those two go away, but we're left with 2y prime squared. And then what else we got? Just minus 8 equals 0. So that got a lot simpler. And now get the 8 over. And then to simplify, or to get this in standard form, we got to get a 1 over at the right. So we're going to divide everything by 8. So that gives us 5x prime squared over 4, because it's 10 over 8 reduces to 5 over 4. 2 over 8 reduces to 1 over 4, so plus y prime squared over 4 equals 1. Almost there. If you'll remember, when we do these, we can't have anything on top with this x squared. So what we've got to do is divide it again by 5. So what this gives us is x prime squared divided by 4/5 plus y prime squared over 4 equals 1. And now we have finally got our conic in standard form. Identify it. It's got a plus in the middle. Must be an ellipse. The bigger number is under the y. So a squared is 4. And since it's under the y, then that means our major axis is vertical. Okay? So let's graph this thing. The center is at 0, 0. Thank goodness. All of these will be. We would not make it that much more complicated. Oh my gosh. Okay, and so the vertices, since a squared is 4, a is 2, so the vertices, since the axis is vertical, then we're going up and down. So they must be at 0, -2, and 0, 2. We'll call them minor vertices, will be where b squared is 4/5. And the square root of 4/5 is approximately 0.9. So they would be -0.90 and 0.90. So to go over and graph this thing, my rotation is 30 degrees. So I don't know, what is that exactly? Oh, okay. I think it's right here. So there's x prime. And so y prime will be there. Okay. So our vertices, let me just take this over here so I don't have to keep going back and forth. put it on the page before. Okay, so our vertices were at 0, -2, and 0, 2. But we've rotated. So I'm not going to go straight down. I've got to kind of curve a little bit, okay? So we'll be about there and about there. Again, you're not having to graph these by hand, but you do get the idea that I can't just go straight down since I'm rotating like a circle, I hope. Okay, and then the other two, oh, I graphed those wrong, of course. 0, -2, and 0, 2. So about there and there. And so the other two were about 0.9 and -0.9. So there would be -0.9. So we'll come down to about right there. And then positive 0.9 might be something like that. And so now I can graph my ellipse. Okay, so we have finally finished example 6. For example 7, it says, identify the conic section without rotating the axes. So this is when you've got the BXY in there, okay? And the ones before, the first few examples we looked at, the BXY wasn't there. So with the BXY inside, it's a parabola if b squared minus 4ac equals 0. It's an ellipse or a circle if b squared minus 4ac is less than 0. And it's a hyperbola if b squared minus 4ac is greater than 0. So this says identify the graph. So A is 3. B is -2 square root of 3. And C is 1. And so we plug into b squared minus 4ac. Sounds familiar, doesn't it? So -2 root 3 squared minus 4 times 3 times 1 will give us, let's see, root 3 squared is 3. And -2 squared is 4, so 4 times 3 is 12. And then -4 times 3 times 1 is -12. That gives us 0. So according to this, then we must have a parabola. Okay, now this concludes our section on rotation of axes. I may try to make another example, but basically if you go back to example 6, if you didn't catch on the first time, watch the video again through example 6. All of them will look like example 6, whether it's a ellipse, hyperbola, or parabola, they will follow the exact same process. So if you didn't follow what I did the first time, go through and watch it again. Go through and watch it while you do your examples, or look at the notes that you've printed out that I provide for you while you work your problems. Okay? So that concludes rotation of axes.